works, let's start to take a look at example 3. So again, we're going to solve systems of nonlinear equations, but this time we're going to look at what happens when a circle meets an ellipse. And there are a bunch of options, right? So I provided the visuals. The ellipse might not ever intersect the circle. It might intersect once, twice, 3 times, or 4 times. So there's just a ton of options. Well, by a ton, I mean 5. And I can't tell on site, like we're going to look at example 3 in a moment when I scooch the page up. I wouldn't be able to tell by just looking at the equations if it was a 0, 1, 2, 3, or 4 solution type of system. But I'll use my algebra to get there. So let me scooch this up, and then we're going to attack this problem using elimination this time. Now, if you want to use substitution, you're more than welcome to. You could solve this equation for x squared and sub it in here. You could solve this equation for y squared and sub it in here. You could solve this one for x squared, sub it in here. This one for y squared, sub it in here. So you could absolutely solve this by substitution. I want you to hear that. But just for the sake of practicing elimination, I'm going to solve this with elimination, and I'm going to opt to knock out the y's. So I see I've got positive y squared and positive y squared here. And if I could change this to a negative y squared, if I could change all of these signs, and I will in a moment, I could add those two equations together and the y would eliminate. So I'm going to go ahead and multiply this bottom equation by -1 and then add them together. Alternatively to that, if I wanted to eliminate the x variable, I could have also multiplied this bottom equation by -4 and added them together, and that would have eliminated the x squared variable. So that's also a very viable option. But I want to pick the smallest numbers I can, so I'm going to multiply everything by -1. The x squared, the y squared, and the 10. And if I do that, that would change this second equation into -x squared minus y squared equaling -10. So let me go ahead and rewrite my system. All right, I'm going to put a little bit of separation here. So let's say I had 4x squared plus y squared equaling 13. And I also have -x squared minus y squared is equal to -10. If that's my new system, because I've multiplied this by a constant, and since I multiplied left and right side, I haven't changed the equal sign. It's still equal. But now I have y squareds, same coefficient in front of them, both 1, but one's a positive 1, one's a -1. I can add these together, and by design, the y's will eliminate. And what do we have? 4x squared minus x squared is 3x squared. That will be equal to 13 minus 10, which is 3. And then I start to solve for x, right? I'm going to divide both sides by 3, and that's going to get me x squared equaling 1. And there's a couple of ways you can solve this. You can take the square root of both sides, right? And you would arrive at x equaling plus or minus 1. Maybe you move the 1 to the other side and then you factor it. I think this would be the longer way of doing it, right? But you still arrive at either x minus 1 is 0, so x is 1, or x plus 1 is 0, x is -1. A faster way would have just been to square root both sides and say x is plus or minus 1. But I just want you to see both are working, right? You also could have taken this equation and used the quadratic formula, right? Bunches of ways to do this. Okay, but I have x equaling 1 and -1. That's great, but I need ordered pairs. So let's go figure out what happens when x equals 1. I'm going to look at this case, see if I can find the y values. All right, and I know, and I'm going to use this one. I'm going to use the fact that x squared plus y squared is 10 and solve for y. So instead of x squared, I'm going to have 1 squared plus y squared equaling 10, right? X squared plus y squared is 10. Well, what happens when x is 1? 1 squared is 1. And if I move that 1 over, I'm going to get y squared equaling 9, which is awesome in that when I take the square root of 9, it's a whole number. Even if it wasn't a whole number, it would be fine. The answer would still be the answer. But whenever you square root that variable term, right, square root of y squared, that's when the plus or minus is going to show up. So here I have 2 ordered pairs. I have 1, 3, and 1, -3, right? So I have at least 2 solutions so far. Okay, and we'll see what happens when x is -1. Let's try it when x is -1 and see what happens. All right, so then I would have -1 squared plus y squared equaling 10, but -1 squared is also 1. right? I'm still looking at y squared, excuse me, 1 plus y squared equaling 10. So y squared again is 9, which again leads me to y is plus or minus 3. So I actually picked up two new ordered pairs, -1, 3, and -1, -3. So these 4 points wind up being the 4 solutions to my system of nonlinear equations, right? So if I have some space, I think I do. Let me put one more little separation bar. My end game answer here looks like it was 1, 3, 1, -3, -1, 3, and -1, -3. And for these problems, the equations are starting to get more convoluted, and it's not really worth me putting it into my calculator at this point. What I could do is I could check it by plugging in 1 and 3 and seeing if equality holds, right? If x is 1, 4 times 1 squared is 4. If y is 3, y squared is 9, right? 4 plus 9 is 13. So that's looking good. And the negative here on this second order pair won't ultimately matter because it'll be squared. But let's try 1 and 3 down here, right? 1 squared is 1, 3 squared is 9, 1 plus 9 is 10. So I'm happy with all 4 of these solutions, okay? All right, thanks so much, everyone. Bye.